that's Professor Janos Sztipanovits from Vanderbilt University. He's very well known in this whole area. He is the Bronze Honorary Distinguished Professor of Engineering at Vanderbilt. He's the founding director of the Institute for Software Integrated Systems there, ISIS. And then currently he works on the foundational applications of model-integrated computing, cyber physical systems. He's done a lot of work in adaptive, structural adaptive systems, autonomous systems, software operations, for design technology. He was the program manager at DARPA several years ago in DARPA ICO. He was the founding chair of the ASEAN Special Intergroup on Embedded Systems, Embedded Software, SIGBED. He's a fellow of the IEEE, and he's an external member of the Hungarian Academy of Science. As you mentioned before, I guess from the name, he's from Hungary. He got his graduation from summa cum laude from Tenn University of Budapest in 1970, and he's a doctorate from the Hungarian Academy of Science in 1980. So we have had long collaboration with Janos through the years, and we got together one large CPS from inside. So it's very appropriate that he's here to talk to us about model integration challenges in design of cyber physical systems. The slide has changed a little bit, but the topic is the same. So,
thanks, Jan. Thank you very much for the invitation. So let me all right, so let me talk to you about an aspect of model-based design that came up mainly in this whole cyber physical system context. Much of the things that I describe relate to work what we are doing right now with DARPA in the program. But occasionally I will take a round towards other areas as well. So as you know, cyber physical systems, it's a rapidly emerging cross-disciplinary field, and it's really interesting in a sense that a lot of formal methods is required, driven by challenges in model-based design, system verification, and primarily pushed by this DARPA program, manufacturing and system integration. The big dream is that we can do down the road full model-based design in the sense as the VLSI industry did that, which enables that different kind of models of the chips can be developed, formally verified, and taken to weblines that replicate it with a good deal of behavioral predictability. And whether or not it will, that success can be repeated, which ultimately resulted in the separation of design houses from the fab houses or the foundries. It's a big question because the DARPA program is actually going after this. Now, what I will do in this presentation is that I will talk first about the cyber physical systems topic from the point of view of modeling languages. And one of the key issues which will come up, where I would like to make my argument, that from a modeling language point of view, the cyber physical system bring in the model integration challenge with vengeance. And that creates a quite interesting situation because we cannot afford anymore that we use modeling languages where the semantics is not explicitly designed, but basically it's a gentleman agreement among the folks who are using a particular kind of modeling language or modeling language standard. Of course, the cost of that is pretty significant, and most importantly, the cost is that we have to deal somehow with the semantics and the formal specification of the semantics of these languages. So I will talk about our take on it, specifically structural and behavioral semantics. I relatively quickly browsing through the whole presentation material has references at the end of it with papers, so I refer to many of these things at the papers. And then I will go to the third topic, which is now how can we use in practice formal semantics and what kind of impact we can make on the infrastructure and the design automation practice what we use. So this is my plan. Now let's talk about the whole model-based design idea. As you know, model-based design means that that you want to use models in domain-specific design flows, and ultimately your purpose is that the models and modeling language are rich enough and complete enough that after going through on the model-based design process, you can get the design to production facilities and product comes down to work as the whole process promised to work. There are many examples of this. Usually these examples are built up for relatively narrow domains. Think about Simulink state flow or many of these narrowly pitched modeling environment and system generation environment. Usually they build up such that they put together really a specific domain-specific tool chains which has it links to some kind of mathematical and physical foundation, and they build basically the overall tool infrastructure for that particular purpose. What's the problem with this? The problem with this is that the cost of building these things is pretty massive. If you want to repeat the success in other domains, then you usually have to rebuild the tools, which is in most cases cost prohibitive. It conflicts with the problem, with the other well-known fact that if you want to generalize your modeling languages, then you start using abstractions that are not specific to the domains. You lose a lot of advantage. So ultimately that leads to these separated islands of automation for very specific domains without any linkage across. That's pretty much the current situation in many cases. Now this is what we are advocating for. Instead of doing the review structure, which is using just dedicated domain-specific tools around the whole process, we introduce another layer. These are the metaprogrammable tools and environments related to metamodels. We call them different names. But let's visualize it such that these metaprogrammable tools and environments together with the metamodels and together with the different complementary tools create basically a semantic backplane on the top of which you can create these highly customized domain-specific environments. Of course, that agenda requires that you provide a solid semantics for metamodeling, metaprograms, semantic specifications. And not only that, but also you have to have these metaprogrammable tool suites where using metamodels you can customize the individual high-value tools to work these narrowly pitched domains as you like. If you do that, it changes significantly the view how you define your agenda for creating domain-specific modeling and for creating, in general, model-based or pursuing model-based design. If your infrastructure allows it, because it's effective enough, it's semantically solid enough, then it turns out that designing the abstractions, the modeling languages, can be also part of the design objectives. And that's a significant shift from the heavy-duty, massive, standardization-based modeling languages, universal modeling languages. It pushes you toward a much more agile concept of design automation. I may not go into that perfectly. Obviously, standardization plays a major role here, but perhaps on a different level. Now, if you look at that structure, you see that for building that middle layer require quite massive software efforts. You need to have these meta-programmable model building, model transformation, model management, tool integration infrastructures. We have one of these. It evolved during the last 15 years, so it was a significant software effort. There is a repository, which is it's open source and downloadable. So many people use that now all over the world. We also have to deal with, based on the existence of this meta-programmable layer or meta level, the foundations of defining semantics. And I will go into the details soon. We do it such that we separated the so-called structural and behavioral semantics, and we have the appropriate tools to define structural and semantics and behavioral semantics for these different modeling languages. Ultimately, the goal is that with these meta-programmable tools, you will be allowed to use always the simplest possible domain-specific modeling language, what your problem requires. And the second, you construct these modeling languages not necessarily totally from scratch, but using libraries. But these libraries are libraries what you construct, what you use for constructing modeling languages. Okay, so these are elementary, how to say, basic modeling language libraries, or modeling language construction libraries. Now let me go into another topic. How does it play in a cyber physical design problem, what we started dealing with? Here is a list of components what you deal with when you have to work with cyber physical systems. We came from the software area, so for us it was not surprising, but it was kind of rude awakening. The components are things like engines, transmissions, battery, vehicle management systems. The vehicle management systems internally are decomposed into massive software structure, software components, hardware components. There are servos, linkages. So altogether, if you look at the scope of these components, you see that they span multiple physics domains. So multiple physics, multiple design domains, and of course a variety of tools where these different components or the models of these components are represented. The thermal models, for example, for engines use a particular type of tools, which is totally different, of course, from the Tenn models, which is totally different from the dynamics models and so forth. So heterogeneity everywhere, on every conceivable level. Now, if you look at that challenge, first of all, you observe that there are indeed physical subdomains, there are cyber subdomains, they are totally mixed cyber and physical subdomains. If you look at that challenge, what is your first instinct? The first instinct would be that, fantastic. This gives me an opportunity, if I have meta-programmable tools, to define now the modeling language for cyber physical systems. But you soon realize that it would be totally impossible. It's impossible because much of your assets, what you have to reuse, are already existing, hopefully, because otherwise the whole thing is dead anyway. Much of these assets existing in model databases that are built around tools, thermal modeling tool, Simulink, and all of these things. You don't have a choice. You actually have to deal with this. And you have to deal with this such that you learn how to build up an integrated environment where you have to deal with the interactions across these domains, such that the different elements, the different models are coming from many different kind of native representations. So just repeating it, if you look at a notional design flow for cyber-physical system, you know that that's typically structured the following way. You do architecture design. In the architecture design phase, it's often called conceptual design phase. You do rapid design space exploration. You use in this phase design space models, architecture models. You overload the design. You overlay the design space different constraints. Usually the models here, low resolution models. You're not even necessarily going to behavioral models, which possibly capture some of the behavioral characterization, but not detailed dynamics. And what you have to do here to rapidly build different behavioral configurations or the system configuration and see the first rough cut that what are the basic configuration which would satisfy my needs. The second is an integrated multi-physics and cyber design. Now you start dealing with dynamics. But this dynamics is primarily long parameter dynamics. You have to do here the design space exploration such that you take over here all of those basic configurations, possibly hundreds of them, that satisfy your primary design requirements, and then you take those configuration specifications, hopefully rapidly synthesize the long parameter dynamics models, and then you run studies. You run basically simulation-based verifications or reachability analysis, not necessarily simulation-based reachability analysis for safety requirements. And circulating that loop, which again includes appropriate modeling, usually compositional modeling, which is automated generation of these models, then simulation, BMV, and proceed. And then finally, there's the detailed design when you have to go to first principle-based physics modelings, which includes, of course, the CAD models, finite element models, and whatever essential physical requirements or the essential requirements are there. These first principle-based models are also used for generating for this medium phase where you can still do rapid design space exploration, different proxy models, which is some abstraction of the high fidelity physics-based models. So something like this would be required. And when you go through on the design flow, you clearly cross across a variety of subdomains, and ultimately you start facing the problem or what to do with the modeling languages. I don't want to go through on all of these in details. The next two slides are just excerpts from the different domain-specific modeling languages what we started using in the Meta program. These are architecture modeling languages that do, of course, hierarchical model interconnect. This defines components, interfaces, interconnects, parameters, properties. As if you would select some aspect of SysML. I know the structural aspect of SysML, what you all know. Yeah, you can expand that or enrich it with design space modeling, where you can add to these structural models constructs with which you can build spaces, design spaces. And these constructs primarily are alternatives, hierarchically layered alternatives, parameterizations, and of course you shape the overall space using constraints, what you overlay for this. Now, you can go on and start dealing with dynamics. Here, if you have multiple physics, what presses you is that you have to model the system, the physical interactions, physical dynamics, not in an isolation, let's say electrical, mechanical, and other. but you have to be able to model the interactions across these physical domains. So in that sense, it's worthwhile to use a modeling language which has the nature of being multi-physical, where you can capture easily in a kind of native way these cross-physical interactions. And the modeling language was what we use is bond graphs. It has a very well-defined, well-defined semantics. It's being used for a long time. Yeah.
Does hybrid bond graphs mean across domains? Is that what hybrid means in this context?
No, the bond graph is multi-physics, and in that sense hybrid. A hybrid bond graph means that you can enrich the bond graph representations with switches with which you can model hybrid dynamics also.
Okay.
So that's
Yeah.
So that's one interesting modeling language, and I just described for you what are the motivation why we are using hybrid bond graphs. An interesting feature of these bond graphs that you can take these bond graph representations. It was developed in the 60s, I guess, at MIT. And you take these bond graphs and you can compile them into or do model transformation, and you can generate different kind of representations that can be solved by underlying solvers. So you can, for example, translate them into Simulink, and you can translate them in Modelica if you wish. I will talk about it later. Then comes the dynamics in terms of the computation, the cyber components. That's in itself pretty rich. You have to use modeling languages like data flow-oriented, state flow-oriented languages. You make decisions what kind of software component model you use. Let's say we use here time-triggered component models. And you model here input, sensor input, software assembly structure, actuators, processor topology, the mapping across them. So, you know, basically what you do whenever you model embedded controllers and the connection to the
Where is the time semantic in these two blocks?
I will cover that pretty nicely. So the timing semantics from the cyber element is in that particular component, in the component modeling, the specification of the software component model what you use. So for example, that TT means that what we use in this program is time-triggered. And the underlying composition platform is a time-triggered composition platform, and we use TT, Ethernet, and that kind of stuff. Unfortunately, this is not enough. You have more modeling languages. CAD is a major issue. And in CAD, what's an interesting challenge that if you have the specification of an overall system configuration, which let's say tells that I want to connect to this engine, this transmission, you have to be able to, through the geometric interface, synthesize the integrated CAD structure.
So one of the things we have come across, and this is this question I had already, is that we have been asked to provide appropriate geometric indexing for integration.
Right.
Because in many of these things, there are geometric variables or descriptions that
That's
have
right.
too much, and they
That's
are
right.
linkages.
That's right. So there are geometric constraints at the geometric interfaces. You have to look at these constraints, and basically when you compose the CAD
switches in the
models.
wrong place with the engine.
That's right.
Like that.
Right. Now, CAD tools where we use. Let's see. Here it will be on some of the slides. So CAD tools help you to define these constraints, geometric constraints, but you still need to do a bunch of legwork until you get to the point that you can automatically generate the integrated CAD models. And then comes an additional area which we just start working on, and this is the manufacturing related modeling. You know, whenever that task comes up, that you have to, or you try to separate design and the design houses basically from manufacturing, the fabs, what does it mean, the separation? Separation means that you have to explicitly model the manufacturing related constraints, what you build in the design.
And the processes.
And the processes,
So
right.
you used to make.
That's right. And what's the manifestation of that? What are the constraints, what that costs, that imposes on the design process? If you don't do that, then comes that situation which is very common in BOD, that the reference contractors are basically doing their design on their own manufacturing capabilities, and after that it's basically unmovable.
My favorite example is you were running with, where I'm trying to fix something in my car and I cannot reach it.
Right. So now really there is a part of the program we started up which deals with fabrication, and this is an interesting challenge to see what kind of hands-off between the two domains can be built up. So we already have constraints related to manufacturing uncertainties, materials, of course.
What is used to study the linkage between these 6 blocks? Because they are not independent.
So they are so right now there are no well-defined
If you
interfaces.
stay here, right, for instance, there are very solid connections between manufacturing models and geometry, right?
That's right. That's right.
People here have studied, I mean, escape route and talking, right, about whether something is manufacturable and
That's right.
reach it or whatever.
So we have we are working on the design size. We have a bag of opportunities with which we can, of course, constrain size through parameters. We can constrain the geometry regarding what kind of fixtures you can use. But there are a bunch of other things, particularly in the 3D world, that the manufacturing guys really don't have a clue yet, and we don't have a clue. So there will be a lot of interaction now how to manage these two worlds, and how to enrich basically manufacturing related elements, the overall design. Where we have a better understanding is cost and cost-based design space thinking. So we already demonstrated this that in the early design space exploration we can rapidly generate some basic manufacturing operations, types of operations, and they are this so-called seal tool that let you to capture all of the costing for that, and with cost we can trim the early design space. So
Is the cost model component based, or you actually
it's
have
component based. It's
so
component based.
prices per components? You don't have models that
And that's something I'll do
but they can take into account the manpower costs and the scaling costs and all that. So there's formulas, not just the components.
So there are manufacturing, elementary manufacturing operations, and these operations are costed. And based on that, if you have a basic configuration of the system, you can have a very rudimentary
Because when
assessment.
we did the design for cost back in the late 80s and 90s, the thing we could not get is the cost models that the companies were using internally for the different components. So, but I guess the way it's built allows the linkers to proprietary cost models.
Yes, yeah, in a sense that if you want, you can do proprietary data.
In other words,
but,
the interoperability is a requirement for the overall thing from the very
right.
beginning.
Yes, that's right. That's right. And yeah. But interoperability already exists, but what the data manipulated is, it's
So you have something like an API where I can link my cost program.
That's
and
right.
use the rest of the
That's
stuff with
right.
my cost program, and I don't have to disclose that.
So altogether, what's the model integrations challenge? So one, what we were talking about, the heterogeneity of physics, right? And you understand that that the issue here is not that they are electrical domain, mechanical, hydraulic, and thermal, and so forth, but the fact that they can interact. And these separations which exist right now across these domains and captured in different kind of tools needs to be resolved. And the second is heterogeneity in terms of layers, implementation layers, that comes in with, well, with force in the cyber physical, in the cyber aspect of the design when, let's say, you come to the point that you design your physical dynamics, you have the plant dynamics, you have the controller dynamics, but then you use a layered implementation, and in the layer implementation you use, of course, for the embedded controller something. So you, for that you have to use a totally different kind of abstraction for representing modeling the software components, modeling the system and platform, and ultimately the system and the platform together with the software will approximate that kind of continuous dynamics what you would like to have in the embedded controller. Now to understand these kind of interactions and what this is called the leaky abstractions, what kind of problems it causes that you just approximate those abstractions that are used in the physical design. So that's becoming a major issue. And in our project with John, we address very heavily this aspect of the heterogeneity.
But nothing is perfectly decomposable.
Right.
And when you approximate, we have to somehow account for what you do.
Now, this is ultimately what captures the approach what we follow in combining together all of these different models. We decided early on that if you look all of these modeling languages, there is no chance that we can survive by creating a meta cyber physical design language, which is the union of all of the modeling languages that we have used. It's impossible simply because it's not a closed set. It will change continuously. So ultimately, what we decided to do that we understand, based on the product category, that what kind of interactions we need to capture, and the nature of those interactions can be much less complicated than the individual models and modeling languages that are encapsulated in the design tool, in the domain-specific design. We capture that in a so-called semantic interface, and through that semantic interface, which filters out those kind of information from a particular modeling environment that are necessary for describing the interactions. We designed this model integration language which does that combination, and it's rich enough to represent the interaction, but not more. And that's basically the approach what we follow. It means that this model integration language is not a set language. It will change. It will evolve. Some aspects of that language are static. They belong to the core. Particularly some of the structure aspects. But as different modeling principles are coming, it will expand, it will be morphed. Now you can do that, of course, if you have solid underpinning, solid semantic foundations for composing a language like this from elements. And that's a leading indicator. Why do we need to deal with semantics, and what do we mean by semantics? So let me talk about this. That composition occurs in this semantic backplane, and I don't want to waste too much more time. But I guess you understand what we are after. Okay, a few words about formal semantics of DSNRs. And some argument what was important for us to reason for the others in the program. Why to do that and what we can expect. So why do you use formal semantics? One reason for using formal semantics is to specify the semantics, right? That's that just belongs to the good hygiene. That's practiced many times. When you look at 30 plus variations of state flow semantics, you can find a whole variety of methods that are used for specification of it. Now, if you use the specification, you can use a variety of methods for specifying it. The important thing is that it has to be solid enough. But another reason why you are using why you are doing is to unambiguate, which means if there are alternative semantic interpretations, then you have to show the differences between them. In that case, you have an additional constraint that you have to use a formal framework which is the same for these different kind of semantic specifications. And the next step is that you want to compute with it. And computing with it means that your semantics has to be not only precise, but manipulable. And we are very heavy after that, because we want to do things with it. So we went after those methods where that works. Now, if you look at the domain-specific modeling languages area, then you know that basically models represent two kinds of things. That's in engineering we associated these two things. One is the structure, which is the logical, physical structure of the thing, and the other one is the behavior. Right? Now, it's not necessarily true that all models have behavioral semantics, right? Occasionally, it's perfectly enough just to talk about the structure, how things look like, right? Without how they behave. Right? Occasionally, this is very tightly coupled. Typically, we deal with the structure modification in design to achieve a certain kind of behavior. Right? But ultimately, this pair, the structure and the behavior, is the holy thing in engineering. That's very heavily ingrained in our thinking. So it means that it makes sense to deal with them separately, or identify these two things separately while we are defining semantics. Now, if you look the semantics that belongs to the structure, what would you expect there? The structure semantics mean a set of well-formed model structures. So basically, it's the definition of a possibly complicated set, which includes all of the well-formed model structures. Now, if you want to express that, you can choose different mathematical domains. One mathematical domain can be graphs, graph theory. Another mathematical domain, what we use now more and more, is term algebra plus logic. It's particularly interesting for why would we want that? Basically because we want to compute with it, right? So, if you use term algebra plus logic, particularly some kind of logic programming framework which has immediately execution semantics, then you can really go such that you not only specify the structure semantics but compute with it. I will show you what we compute with it. Regarding the behavioral semantics, there are two different styles, but you can proceed. One is the denotational style, and the other one is the operational style. Should we choose one of those? No way, because there are so many different kind of things that you have to understand both, and just use whatever is the most feasible. Here is some examples. So now let me think over, because it's 45. Let me get going with this part, because that clarifies the conceptual things, what we are doing, and you can see the details in papers and other things. So here is an example. So we have structural and behavioral semantics in these two styles, and let's deal with the structural semantics first. So here is a physical structure of a system. That physical structure is using some kind of made-up notation, but you see that's a physical structure. It has resistors, inductors, some kind of physical structure what I combine together. Now, what can I do? I can take that physical structure, and if I know the structural semantics, and I have the machinery, what's provided by structural semantics, for example, model transformations, which let me to translate one structure to another structure, I can take that physical semantics with a nice diagram, which is understandable to everyone, and I can translate it through a transformation to another model structure. And that model structure will not be understandable by everyone. This is a bond graph model structure. But the advantage of this, that bond graph model structure, which again can be directly composed from this physical structure model, now represents all of the energy flows in the system on that level of fidelity, what I need. And I can deal with this further, for more specific things. And that's the exciting point, that now I can talk about behavior. So I start building up the relationship.
This is the energy view of the system.
That's the energy view of the system, but that energy view was just describing how the system looks like, but it didn't tell you how it really works.
Another view.
That's right. Now let's see what kind of, what else can I do? I might decide that now I use the bond graph model to do and to use denotational semantics to tell what is that behavior. And indeed, from bond graphs, you can do a translation, another model transformation, and generate the ODEs, which describe now in the form of an ODE what is the behavior of that system, what you described there. And that's again a set of mathematical equations. But you can do different things. You can take the same bond graph model, and you can do a transformation, and you can put together a Simulink model. It's non-trivial. It requires more things because you know that Simulink is using input-output kind of language. You have to deal with causality resolution and so forth, but that all can be computed. And we can indeed compute the bond graph model into a Simulink model. And if you have a Simulink model, then you can do what? You can do operational semantic specification. You can just generate trajectories based on that. So now I have, for the same system, two different kinds of representation. One is a more operational style representation, what I don't show here, that the Simulink simulation engine will operationalize for me that model, and will generate for me the trajectories. And here I have a denotational semantics, and I can give it to my favorite solver. For example, I can package it together into a Modelica model and give it to Modelica to deal with this. It's just, so in this area, semantics of modeling languages, there's a huge history, long history I just named. It's not the semantics in general, because otherwise, of course, Miller should be here, but these are just really the modeling language papers and milestones. Let me just skip that. Now, in the next few slides in the lecture, I showed examples for, not example, I basically went through briefly what do we do with structural semantics and what do we do with behavioral semantics. Let me just jump through a bunch of things here. The bottom line is that the structural semantics, when you deal with structural semantics, what you have to solve that you have to find a mathematical domain where you can, in a very high fidelity, complex structures can be there's complex structures, complex sets can be built up. Thermal algebra gives you a way to build up elements or to define elements in an elegant way of sets, and if you put on the top of it some kind of logic, and what we started using, what basically my students started using, this is his thesis work, was first he used prolog horn logic first, and then later he changed over to already at Microsoft first order logic equivalent logic programming framework. Now you can do with this environment really interesting things, and let me just show what can you do if you set up all of these things. You can do conformance testing. So you can tell, this is my model. Tell me that model is element of the domain or not. Okay, that's easy. You can do non-emptiness checking. Non-emptiness checking is important because it means that if you compose languages, composing languages now gets a really very specific mathematical meaning. You really can create situations when there are internal inconsistencies such that you cannot ever satisfy the constraints that belong to it. You can do, of course, DSML composition. There are these categoric theory-like composition of categories for domain composition. A very interesting thing, you can do model finding. You can create a partial model, and then you can issue a query and tell the system, complete me that model. And it gives you back a satisfying solution for this. And finally, you can do transformation, specification of model transformation, using some kind of techniques in that system. It's basically a term rewriting process. Now, it's worthwhile also to mention that, first of all, we have papers describing the origins of this, but Microsoft now has a tool which is distributed now with Visual Studio, and you can download it. It's without cost, so you have to go to, I guess it's somewhere in the page, you have to go to Microsoft Research and Formula, and there is a full tool suite for that. And it's very actively building, so it's very nicely evolving. Now, how we use it? We have our modeling environment. This is the GME, the generic modeling environment. It has the meta modeling part, the domain modeling part. We have the compilers with which you can translate the meta models or the models into formula. In formula, then you can play out these games. So you can study, you can do analysis, you can see what is the impact if I compose the modeling languages. So ultimately, your primary tool for, let's say, composing modeling languages and doing these validation studies is not formula, but you define it on a high level in your usual format, and then formula is used as an underlying engine to do these kind of things.
So what happens if I change my constraints in the end?
Yeah, then you have to again recompile the model.
So change the constraint, recompile,
and it refines the formula domain. Then they don't have yet that we can incrementally add new constraints.
So my understanding of physics changes. I now have better presence. I want to be able to have added two constraints to get a better set of models. That's my question.
All right, here's a slide which describes what's going on with formula. We work quite extensively with Microsoft on this. Behavioral semantics, only one thing about behavioral semantics. When you want to deal with the specification of behavioral semantics, you can do the following. That's what the style what we are pursuing. You have the model, you have let's say an internal representation of the model like in the form of an abstract syntax tree, and then you can write a model interpreter and you translate that model into an executable model, let's say into a simulatable model. So that's one way to do it. The problem with that type of specification of behavioral semantics is that you push all of the non-declarative complex stuff into the model interpreter code, and if it is C++, then you cannot reason too much about that. The other path is that you select an appropriate mathematical domain, in that case, let's say graph representations. You can express them, the model transformation using graph rewriting rules, and from there you can generate various things, or input for an executable model, executable code, or an executable specification. That's the path what we worked out up to this point, and we have all of the tools for this. The executable specification, it's an interesting issue here. We used a framework which is called abstract state machines. That's again a Microsoft tool. The abstract state machines are a good specification language. It's at a very high level, doesn't have any kind of implementation.
But does it have a problem with tracking distributed implementation?
No, in the abstract state machines, you can model distributed implementations. You can. Right.
We need to discuss that because the logic changes.
Now, there's another point that we slowly migrate away from this path, what we worked out, and we start going more and more to the logic, because it turns out that formula now is rich enough that we can define the model transformation in logic. And that gives us a tremendous power to reason about properties before adopted the model transformation. And that's an active area.
Is the abstract state machine on Microsoft evolving, or it's fixed? It's all stuff.
It's no, it's not evolving. So it's they did it the way they kept it alive until we asked it. But now frankly, we are drifting more towards formula-based representations. Still, we have all of the implementations for the religious stuff, but it's not evolving anymore. All right. Here are some examples how to do that, how to use that. Now, some words finally about how we use in practice these different semantic specifications. Again, coming back to the avian models. So one issue is where the semantics is coming from. And when you deal with cyber physical systems, one interesting source of semantics is physics, basic physics laws, and that's very important because I quoted here Kalman, who told that that if you want to do well in modeling, get the physics right, and the rest is just mathematics. And indeed, the lesson is for us that if there are physical laws that your models need to satisfy, it's worthwhile to capture those into some kind of form of semantic constraints and build into your tools.
Except he said that you're going to get about destruction.
Okay, so let's see how we do this kind of things. One example, structural implications. We have here our previous example that we had, that rotating mass and the electric motor, and we want to build up the bond graph for this, the energy representation. In that notation, in the bond graph notation, you have, of course, the electric domain and the mechanical domain. You have these two physics domains that are linked together. There are ports and everything, and you want to compose them. You want to put in a link, but that link relates to an electric port and a mechanical port. That's impossible. You have to prevent this because it's physically meaningless. So what you have to do here is that your tool recognizes that because you want to link two physics domains, you have to put in a gyrator. This is all bond graph semantics related things, but it's conceived by physical laws. So that's the nice thing. And that relates to the energy conservation law. And indeed, we build now in our tool suite, which is a metaprogrammable tool suite, these additional physics-based rules that that now is becoming as part of the structural semantics.
And this may actually put the design question, can I have a path that allows me to do it?
That's right.
And you can go into space and say, you make the proposal.
Right.
Those of you who know the work of the guy that did the analog of the guy with the car, with the Lotus car, with Smith, Malcolm Smith. He asked the
Right.
question,
Right.
he came up with a mechanical analog for what we call a capacitor, right?
Right.
And this changed the design of automobiles and the things like that.
But the other thing what we experimented with is the following. So you build again the models for this structure, for this mechanical system here, and you now properly model it, and you realize that, well, I have an electrical source, an electrical circuit part, and it's a dissipative thing. It generates heat. Now, do I need to do anything with that heat? And the question is that, is there any other energy flow between the mass here and the electric part here? And of course, you can build up a reasoning argument that if your axle here is, let's say, metal, and you don't have thermal insulation here, then you have to, first of all, you have to pose this question to the designer, to the modeler, to answer this question, and if there is an energy link, then you have to build that in. And again, that we are experimenting with this, so we don't have complete rule sets, but we have the way to inject in the semantics, in the structural semantics of the modeling tool, modeling tool, these kind of so-called generative rules. Now let's see other. These were all structural semantics related components. What about behavioral semantics? So again, here is our previous diagram, and we have here the physical model. We can translate it into the bond graph model, and now we have the compositional, we build bond graph, and interestingly, the bond graph representation, the physical representation, is satisfying the classical physical laws. There is a one junction rule and there is a zero junction rule. These are basically Kirchhoff's laws. It turns out that because of these rules, you have to put in the generated leaf equation system these constraints. These constraints are explicitly there, so the efforts, the sum of the effort variables is zero, and the flow variables equals with each other. Yeah, right? If this is a particular kind of joint, then it's a one junction. And there are some other alternatives of this rule. So interestingly, even in the behavioral semantics, you have to be able, and you can put in the behavioral semantic specification these additional physics conceived semantic elements that are now where they will be represented. It will be represented in the model transformations, right? And that will.
And most typically, you will end up with the differential algebraic equation.
Right.
In the behavioral model. That's the simplest way, simplest example.
Okay, so it's then there are some other things that related to what we are doing with John, which is how to use how we can decouple these design layers we use for passivity, and interestingly, if you want to restrict the system dynamics to passive structures, then you can enrich your modeling language such that it don't tempt you to do anything else, just passive structures and all that stuff for this. Okay, so let me finish this up. There are few important conclusions of this point for us. One is that we got quite a bit convinced that for these heterogeneous domains, model integration language is a good thing to do, and we try to do the model integration language always such that it's the simplest possible language, which is just needed to describe the essential interactions across these domains, but not more. So that was one thing. The second thing is that that explicit semantics is important, and if you do explicit representation of structural and behavioral semantics, you can use that for enriching your tool suite such that they know more and more about the physics, the nature of the domain what we are working on. And I try to give examples what kind of constructs that you can build in the tools that help you to use that and with semantics. So indeed that law that we want to compute with the semantics is there. So we actively use that. And all of the rest of it is just about how we use model-based design. Okay. Thanks for your attention.
We have time for 2 questions.
I was going to ask about the structural semantics. So have you, correct me if I have the wrong idea, but it seems like there's an analog between structural semantics and what the programming languages community is called static semantics, or where you define high-checking rules and things which are. So is that a correct analogy to think that the
almost. The structural semantics is richer simply because it may be dynamic. So so imagine that you have model structure that are evolving, and the evolution is described by units. So you can have a network, and depending on demand, you have a policy that tells you how you want to expand the network or contract the network. In that case, really the structural semantics is dynamics because you can express these rules as part of your structural semantic specifications as transformations, as elementary transformation. But even more, you can then define constraints that have to be satisfied for the evolution of the structure, such as you are interested only those kind of structures where there is connectivity preserved, and that becoming an invariant. And you express that as a temporal logic form, that property. So, so ultimately the structural semantics is different fundamentally from the so-called static semantics concept simply because it can be dynamic. And we really use that quite a bit for dynamically changing structures and describing structural semantics for changing structures.
How is this framework design exploration fixed? Suppose we discussed it a little bit in the morning. I want to do trade-off analysis where I want to declare marriage constraints or metrics, and I want to change my structural behavior in response to what I'm getting from this trade-off analysis. And I have to understand my, where in the design space I want to be. So you talked about in one of the blocks, design space implementation. How do I say this?
So the we have I didn't talk about that part. We have a tool called desert. The desert is defined for design space exploration and design space proving. The desert knows about our concept of how we build design spaces. It's language independent.
So it's language independent and understands the model.
So language independent, it understands the basic design space construction primitives, hierarchy layer alternatives and parameterization, and constraints over that space. When you have then a particular modeling language, first of all, you can enrich that modeling language with these constructs, meta-modeling constructs, you compose them. Then you get suddenly a modeling language, which doesn't matter whether it's a state machine or a signal flow graph or what. You can now do alternatives and parameterization.
Okay, but does desert allow me to compare with them? Does desert allow me to compare with them?
So-
Constraint satisfaction.
Right. So what?
So I can
what
move to one, it's better or worse.
So what you can do then, that when you build up your models set, which is now not only a single point model, but a design space, and we have a model transformation, which extracts now from that model set only that part of the information which is interesting for design space exploration, which is the leaves out a bunch of other stuff, but it deals with layered alternatives.
It focuses on the options you have.
That's right,
And
and the parameters and the constraints. Maps them, on the other hand, the internal representations of desert, which is beginnings. Okay. And use desert to prove the design space. Then you can do different things. For example, get back all of the satisfying solutions. Give me one of these satisfying solutions, and then proceed.
And desert is restricted to use, decidable inference rules, or if you can get stuck. Are the problems or the computable?
We set it up such that it's computable.
Because
So there are
sometimes you end up
restrictions.
with satisfiability problems and you cannot do it.
Right.
So,
Or the other thing is that it can blow up.
so this is somehow in desert,
It's
even at the expense of losing some value, some power.
Yes,
And so on.
yes.
That's this you have to keep.
right.
Any other questions? Okay, let's thank the speaker. Let me just mention that we have these tools in the same lab, their tools, and since the collaboration is very strong in this area, there are opportunities to visit down there, by the way, if you're a student or whatever, people are going to come in here trying to popularize some of the situations. So thank you for coming. Have a nice evening.
Thank you very much for the